Okay, so we are doing, I think it's 14.3, backstepping. Okay, and name, as the name suggests, we will literally step back, solve for the first portion of the problem, then come down and see. So the so let me just with this example. For example, this is how generally problems can be caused. It's a special case of integrator. For example, let's say we have a state like we were doing in UV. You same here, like you have first six states are position. This next six states are velocity. Your first three are position. Next three are velocity. Right. So eta dot is, for example, f of eta, a general problem, plus g of eta, right, and this is multiply. So your state x is basically eta and zeta, right? Sorry, eta and zeta. Okay, and things will be more clear from example. Generally, when you try to give a mathematical thing, you use more complicated general formulas, right? So, and zeta dot equals to u, right? Now we have to solve this problem. Okay, so the idea is we want to design a state feedback control. What is the goal? What is the objective here? Objective is to find u, means u, such that eta goes to 0 and zeta goes to 0, right? That is the objective, right? We want to take all the states to the origin. That's the goal. It can be a tracking problem. After everything has been formulated such that eta going to 0 means you're in desired position with desired velocity, basically. Right? Desired position with desired velocity. So here, see, you will see, and f and g are known. F and g are known. If they are not known, then you will be applying sliding mode or adaptive. So that's the idea here.
But I thought these, okay, I'll let you finish. I thought you saying backstepping was to help with the sliding.
Yeah, so right now I'm saying f and g are known.
Okay.
Because it is purely backstepping. But if they are not known, you can mix, you will say sliding mode backstepping or backstepping sliding mode, right? So basically the idea is cancellation only, but still we'll get there once we do the problem.
I'll let
We'll
you finish. I'm sorry.
clearly, no, that's a good question. But for now, this is the first step, that pure backstepping, pure, as a technique, assumes f and g to be known.
Okay.
Okay, and then, so let's, if we make a block diagram for this, right, for example, u, the input comes from here, and you integrate, right, u is there, right? So u comes here and you integrate it basically, right? When you integrate it, what do you get? Last set of equations is basically a simple first order integrator, right? So you integrate u and you get zeta,
Yeah.
right? So you get zeta here, and then this goes to g of n, right? Then zeta goes there. So basically zeta now is an input. If you draw this red line here, it's input to the second system, zeta n, right? Zeta n, and then again you if you do the summing up, here is what fn is coming, right? So f, which is f, some function of f, eta comes here, right? So basically the sum of jn and fn is integrated again, right, one more time. So this whole thing is integrated to get the integrator again, you get eta here basically. So this is the kind of, so here you get eta. So this is the kind of function we have. But if you notice, right, we can consider this as this is like, do you remember our cascaded control or inner loop, outer loop kind of things? This is exactly this, right? See, this is one system. This is like, you can say, inner loop system, and this is the outer loop system where zeta, for example, if you wanted to control the yaw, it was you input phi, roll angle. So to yaw, I roll. So I don't know if you remember your UAV dynamics. Your psi dot was g by v 10 phi, right? So phi basically controls your psi, and then psi double dot was something 1 over jx t phi or something, right? So your torque is used to control phi, and then phi is used to control. So something like this. So the output of this is input to the system. Okay, so this is how. So when if you want to use backstepping, this is the type of system you will need. That you should be able to segregate one states, and that the second states can be treated as an input to the other system. So now the basic idea of backstepping is you go first and tell, okay, what I want this eta to go to 0, right? And you think that this is the input, right? Zeta is the input. So you compute for zeta. But what should be zeta desired such that eta goes to 0? And then you step back and say, for that zeta desired, how do I get that zeta desired, which takes eta to 0? You see what I'm saying? So that's the kind of approach you're breaking down. And good thing will be you don't have to guess a Lyapunov candidate function in one shot. You go step by step and add it. Automatically the final candidate function comes out. So there is a, not in that, but also in Lyapunov candidate function choosing, it's a step by step process. Okay? So the idea is to so you break down the problem now. We want to solve this problem first. What is this problem? What if you forget about this, right? That there is something, you just deal with this first equation. So in first equation, zeta is considered as input. So you want to now compute what should be my zeta, what should be that feedback law says that eta goes to 0. Simple as simple as that, right? So there it's easier. Now you can choose your awesome simple Lyapunov candidate function, which is half eta transpose eta or half eta dot square. So, and then we'll go from there. Okay. So now, having said that, so we want to choose our feedback control law zeta, right? So zeta desired, I would say zeta equals to some function of eta, right? That is the goal, right? So I want such that eta goes to 0. Okay, and some this function will be like phi of 0 has to be 0, like when you choose the function. Okay. So let's, the example would have been better, but so now let's say there is some Lyapunov candidate function. Let's because we are just focusing on the first set of equation. What is our first set of equation? It is eta dot equals to, what was that, f of eta plus g of eta into zeta, right? So let's choose some candidate function which is v of eta. It can be something like half eta transpose eta, right? So standard Lyapunov candidate function. But for now we are just taking a general, and it is v of eta, right? So what is v dot eta then? V dot eta will be del v by del eta, right, into f of eta. This equation here, eta dot into eta dot. This is how we compute v dot, right? Del v by del x into x dot. So del v by del eta into eta dot equals to del v by del eta into you can into your f of eta plus g of eta plus zeta, right? Questions? That's v dot, no problem, right? So now what we do, what we want now, we want this to be negative definite, right? We want this to be negative. What do you have in the choice? Let's say this is what I can choose, because this is the input, right? So if this is the input I can choose, for example, so let's say if I choose some so let's say I choose this to be some function phi of eta, which multiplied by this will give me a negative definite. The idea. Things will be clear from my example. I'm just giving a general theory here. Okay. So basically, if I can choose, that means I'm saying del v by del eta. I think it should be transpose so that we can multiply things into f eta plus g eta into phi of eta. Okay. So I have chosen something which makes it negative definite, like minus of omega eta. Okay. So you have to choose in such a way that this overall thing is negative definite. That's the idea. Okay. So this is the ultimate goal. You want zeta to go to this, but in real time it is not that. You want it to be like this, but it is not. You cannot like directly say, hey, this is my heading. You say, oh, you want your heading to be there. So there is a difference between actual heading and a desired heading, right? So you always say, okay, this is my desired heading. So you choose your heading, whatever proportional control, whatever it will turn. So there is some time before your actual states go to desired states, right? So that's the difference here, right? So what we are doing now, so in order to do that, what we will do here is, now let's say we have eta dot. To introduce this term, we go and add and subtract g eta we add and subtract this term gn phi n minus gn phi n eta, right? So basically we added and subtracted this term right now as 0, and I'll tell you why that is there. So now if you do that, then what happens? Eta dot becomes this minus this. So if I take g of f of n eta, so g of eta is outside, it becomes zeta minus phi n. So this is the idea. So you want, this is the error, right? Between, so you want zeta to be this. So I'm giving that, I'm writing this in an error coordinate. So the objective will be to make this term go to 0 also, right? So that zeta can go to phi n. That, and then you have gn of phi n. Okay, so that's there.
So between zeta and phi, which one's the desire, which one's the actual?
So this is the actual, right? This is your actual state.
And phi is the desire.
Phi
Okay.
eta n is that this
Okay.
is what you want, because if z equals to phi n, then this is negative definite, right? If your zeta is equals to phi of eta, then we know that v dot n is negative definite. So you want this zeta to go to this quantity. Got it? Bear with me. So now what you do is, you want to choose a new variable called z, which is zeta minus phi n, right? So if z goes to 0 means zeta went to phi n, and then if zeta goes to phi n, that means the first Lyapunov candidate function is negative definite. That means zeta will go to 0, right? Are you all with me? So for what we are saying, okay, if z goes to 0, then zeta goes to phi n, and then v dot is negative definite. We will call it v1 dot, so that we can later on v1, right? So v1 dot is less than 0. That means eta goes to 0, right? So far, so we have gone from here to there, right? So this, then this, and then this, right? This. Now the question is, how do we make z to 0, right? So that first job is done. That if somehow z goes to 0, then the first term will be taken care of. Now question is, what we can choose to make z to 0. because then z goes to 0, then things are done, right? So now we can rewrite our equations. Eta dot equals to f of n gn. So this goes there, gn phi n. This is the original term, right? This is our original function, plus g eta into z, right? So we have added this additional term here, and then if you see what is my z dot, if I have to compute my z dot now, what is z dot? Z dot will be zeta dot, right? Zeta dot is what? U minus basically phi dot. For now, let's just keep it phi dot. But some, because if in a real problem, I exactly will know what that term is. But for now, let's just. So that's our new equations of motion now, right? Z. So instead of zeta, we have z now. Okay. So we have a new system, and now what you want to do is. One thing I think we want to do here also. So we can once we plug this thing in we can recompute our v1 dot also, right, in terms of z. So v1 dot was equal to minus del v, not minus, sorry, del v1 by del eta into f of n plus gn phi n, right, plus g and z, right? This was the term, right? And this multiplied by this is minus omega 3, right? So minus, or whatever that minus omega plus del v1 by del eta into g and z, right? Transpose. So this multiplied by this is all negative definite, but we have this remaining term which will be made to 0 in the next step. So this remains hanging because z is not 0. If z is 0, then this is minus w. So your v1 dot for now is this, because z is not 0 for now. Okay, so having said that, so now what you do is go ahead and define your, so our v1, now you define v2 now, okay? v2 is v1, which was our previous candidate function, plus half z squared, because now you want to make z to go to 0. Okay, getting my point here? So now let's see, what is v2? v2 dot will be, so it's simple now. See, you made v1 negative definite, you came, so can keep adding, you can, but this will get complicated if your u x1 dot equals to x2, x2 dot equals to x3, and x3 dot equals to u. You see, you have to backstep 2 times. So that will be tricky and a lot of bookkeeping. So if you see, what will be v2 dot will be v1 dot, right, plus z dot, right? So now if I plug it in, so v1 dot is already given here, so let's write that is minus w, which is plus by n transpose into gn of z. And what is z dot? What is z dot? Z dot is u minus phi dot n, right? Got it? Plus there was, yeah. Okay. So now you can see the minus w, and you can go inside and take, because z can come outside, right? So you have z outside, for example, and then you have this del v1 by del eta transport into g eta plus u minus phi dot n, right? Right? Just taking z out, and Okay, now I can choose u. What should be my u such that, see, this is already negative definite. All I want to make it this negative definite. So now I can choose u. Now because I can choose u, I want to I don't know what ugly term that is. I want to cancel that out. I say if u equals to phi dot n, simple, it will cancel it out, right? If I choose u equals to phi n, it will cancel it out. Minus of this, because I want to cancel that out, so minus of del v1 by del eta transpose into g eta, right? And minus kz, some, what will happen? This cancels out, u equals to minus kz, and it becomes, then v2 dot becomes minus w minus kz squared. Awesome. Ladies and gentlemen, we have a controller now. And also, if you see, v2 is the actual, in the first step, if somebody tells you to choose a Lyapunov candidate function like v2 is the combined Lyapunov candidate function, right? Total candidate function, because v2 was v1 plus half z square. So it would have been something like half of whatever eta transpose eta plus this z. What is z? Z is half phi minus, zeta minus phi eta squared. So something like that. You would not have been able to guess this. So you basically build up your Lyapunov candidate function and keep showing at every step that the previous one is negative definite, and the final at the end when you choose u becomes negative definite. So, but this is your controller, as simple as that. And this is the technique, like you have a power now to cancel out. And if things were not known, like gn was not known, you would have used the same sliding mode approach to make it negative definite. Okay, good.
What is phi again?
Phi is some function of eta. It will be clear from example. Like
Okay.
Phi is some function of eta such that the first Lyapunov candidate becomes negative definite.
So phi is something you pick for the first
Yeah.
one? Oh.
Phi
okay.
is something I picked. Yeah, it will be clear. Let's do the example now. But this is the approach. You go step by step. Make sure. Okay, well, it will be fun. Like fourth, fifth order, like you will have to write a code or something to do this, but it will get ugly. Okay, let's do an example. I think there is some example. So x1 dot equals to x1 squared minus x1 cubed plus x2, and then x2 dot equals to u. Okay, so goal is to take x1 and x2 to origin. Okay, so see, now here x2, let's deal with the first equation itself. First equation says x1 dot equals to x1 squared minus x1 cubed. So in this case, x1 is our eta. Okay, right? Minus x1 cubed plus x2. Now I want to choose x2, which is equal to phi of x1, such that the v1 equals to half x1 squared. v1 dot, what is that? x1 dot becomes x1 squared minus x1 cube plus x2. So that becomes x1 cube minus x1 4 plus x2 x1. So what value of x2 should I choose that this Lyapunov candidate function? So that's why I'm saying phi of x1, right? Because so if I choose x2 to be minus x squared, for example, x1 squared, what happens? Right? Minus x1 squared means it will make me x1 cube, and this will cancel out, and this is a good term to have because it becomes negative. So that means, what is phi of x1 then? Phi of x1 is minus x1 squared. That is what phi of eta you told. We picked this term so that the first Lyapunov candidate function, if you put it, will become That's you want, that's the desired, or you can call it x1 desired also. This should be your x1 desired. Oh, sorry, x2 desired, I'm sorry. x2 desired equals to phi of x1 equals to minus of x1 squared. Right? But it is not the case for now, right? It's like, so what you can do is, here, we can add in our first equation, right? We can rewrite it x1 squared minus x1 cube plus x2, and then add this thing here, which is phi of x1 minus phi of x1, right? Add and subtract. Okay, so now it becomes x1 dot squared equals to x1 squared minus x1 cube plus x2 minus phi of x1, right? Phi of x1 is this, but we'll just keep it that way for now, phi of x1. So now this becomes z, right? This thing you can redefine as z, because that's the error. You want your x2 to go to phi of x1, right? So that's the error, z. So you can rewrite it as x1 dot equals to x1 squared minus x1 cube plus phi of x1. That's the original, that's the term plus z, right? See, because v1 dot equals to minus x1 to the power 4 when x2 equals to minus x1 squared. Remember that. Okay. So we can write v1 dot again, right? v1 dot will be, so that's one equation, and also another equation. What will be z dot? Z dot will be x2 dot. So what is z? Z equals to x2 minus phi of x1, right? So z dot will be x2 dot minus phi dot. We'll see what phi dot will be. It's a good idea to keep phi dot as phi dot, so that things don't get complicated at the end, and also good from implementation perspective also, so that otherwise plus minus you will not know at the end what was phi and not. So it's always good idea to keep, like today in the class also I was saying, keep your forces, and people are just writing equations. Just like last slide of that, how would you know what my lift is now, or whether it is negative or not? I'm not doing it. So so it is u minus phi dot, right? And see, if I have to compute phi dot, it was, what is phi dot? Time derivative of minus x1 squared, which will be minus 2x1 x1 dot, right? So we know everything. We can put x1 dot also, whatever that is, not important because we'll cancel it anyhow. So just for the implementation perspective, later on you can compute what is it, but let's keep it phi dot, right? So if I have to write my v1 dot again, which is x1 dot, which is x1 dot is this, right? x1 square minus x1 cube plus phi of x1 plus x1 z. So see, this and this I know is, if you put phi of x1 equals to minus x1 squared, this is nothing but minus x1 4 plus x1 z, right? So that's our v1 dot. So now we can write our new Lyapunov candidate function, where now we want to make z to go to 0, right? So v2 will be v1 plus half z squared, right? Simple. What is v2 dot? v1 dot plus z dot, which is u minus phi dot, right? And which is v2 dot will be minus x1 4 plus x1 z plus z u minus phi dot. Now you can take z common, it will be minus x1 4 plus z into x1 plus u minus phi dot. Okay, now I can choose u equals to minus x1, cancel this out, plus phi dot, cancel whatever that term is, phi dot, and equals to minus kz. Then it becomes v2 dot becomes, if I choose this u, my v2 dot becomes minus of x14 minus of kz squared, which is negative definite, which means x1 goes to 0, and we never showed that our whether x2 goes to 0 or not. We are saying z goes to 0, so let's verify if z goes to 0. When z goes to 0 means x2 minus phi of x1 goes to 0, right? Correct? And also there is a thing that we showed, that we have to choose our function such a way that phi of x1 has to be 0 at x1 equals to 0. Right? Which is the case, right? Because our phi of x1 is what? Minus x1 squared, right? At x1 equals to 0, this is 0. So if you see, x1 is going to 0 for sure, z is going to 0 for sure, and then you see that if x1 is to going to 0, that means phi of x1 is also going to 0, that means x2 is also going to 0, right? So it's a quite, but both your x1 and x2 are going to 0. Understood? Nothing like we did not even use any theorems or something. It's simple addition, subtraction, differentiation. There is nothing fancy here, at least till now. When you use sliding mode, or at least you have to use norms and all to cancel things out, right? But here, nothing. Right? So you can imagine, you can do this for if it is a third order system or fourth order system, things will now if you see your Lyapunov candidate function, right, what is z? So it is equal to half x1 squared, and your z is half x2 minus, that is plus x1 squared. So that is your Lyapunov candidate function, which is, that comes out like in the first time you could not guess that if I choose this Lyapunov candidate function. So this happen because you can choose your u now, right? You can choose u2. At the end step, you can cancel out all the ugly terms. So that is the basis, that this nonlinear cancellation, feedback linearization is what we are doing, right? We are cancelling out unwanted terms and keeping good terms such that the negative definiteness is there, and we know the deal. Okay, questions on this? Our class is till 2:28. 7 more minutes. Let's see if we can do the. Let's do this one. This is right. This is, instead of u, you can say this is x3 desired now, right? Or a function of both phi of x1 and x2, a function of two previous states. Then, so that's what we can do, right? So we'll write it till here. So let's see. Just one more step, right? x1 dot equals to, we could have started at the same point, but let me, so x1 squared minus x1 cube plus x2 dot equals to x3, and x3 dot equals to u. So now your u appears in the third term, right? Like it's like you're controlling the jerk instead of acceleration, right? So position, acceleration. So your input is jerk now. So how do you control the jerk such that the both position goes to desired position, velocity, and then, so that's kind of the very, very powerful tool, if you will, from that perspective, right? So if you see, we were able to get something like, if you just, there x3 was equals to u, right? So you would actually start at the point where you left the previous example. We were saying, okay, that u equals to whatever that was. What was that in the previous? So up till this point we had v1 equals to half x1 squared, right? So v1 dot was minus x14 plus x1z, remember? Let's call it z1 this time. And then you had, and your equations of motion were x1 dot was written as x1 squared minus x1 cube plus x2 and so instead of x2 it was z plus phi of x1, right? Remember? So that was the equation. So it is x1 square minus, I'm just writing the previous one, right? Phi plus z1, sorry. So that is your x1 dot, and then your z1 dot was, in this case it will be x3 minus phi dot of x1, right? Just, and then we're not going further, but we taking v2 equals to half v1 plus half z1 squared, right? And then v2 dot was minus v1 dot, oh sorry, whatever that, v1 dot plus z1 dot, that came out to be, what was that, minus x14 plus z1 outside, I can take x1, and then what was that, this quantity, right? It is x3 minus phi dot of x1. Okay, now at this point, this is v2 dot. Now at this point you can define a new variable saying I want this quantity, because now you're choosing x of 3 instead of you're choosing x of 3. So you're saying my x of 3 desired should be equals to what? Cancel this out, minus of kz. So your x of 3 desired, which is equal to phi of x1, x2 this time, both, right? Equals to, or phi 2 you can call it, equals to, cancel this out, so minus of x1, cancel this out, plus of phi dot x1, phi 1 dot, let's make it phi 1 dot of x1, minus k1z1, right? If I do that, then this becomes minus x14 minus k1z1 squared, right? But unfortunately this is not, but you can then add and subtract this quantity, x3 desired quantity here. So we can do is so now we have to modify this term, right? We are choosing x3 here, so you can say your this equation z1 dot now becomes x3 minus phi dot x1 plus phi 2 x1 x2 minus phi 2 x1 x2, same thing. So you will see that now this x3 minus this phi 2 x1 x2 is minus phi dot x1 plus phi 2 x1 x2. So now you can define this as z2, because if that goes to 0, that means x3 goes to this value, which makes z2 goes to 0, or z1 goes to 0, right? So now your equation z1 dot becomes z2 minus phi dot x1 plus phi 2 x1 x2, which in this case, so now that's the case, and what is z2 dot then? Z2 dot is, this time z2 is this, so this is x3 dot, which is u minus phi 2 dot. Okay, simple. So now we have new equations of motion, and our v2 dot also can be written in this term. v2 dot is now minus x14, and if we plug in So if I put this plus phi2 minus phi2 here, right? So plus phi2 takes that to minus z1 squared, so minus k1 z1 squared, and plus phi2, and minus phi2 basically, minus phi2 means, so plus z1 x1 x3 x3 minus phi2 minus phi dot phi1 dot. So this is basically saying equals to minus x14 minus k1 z1 squared plus, so this becomes z2, right? So that becomes z1 x1 plus z1 z2 minus z1 phi1 dot. That's the new v2 dot. Okay. So this till here we are okay, right? This ugly term comes here. Now we can decide our v3 now. v3 will be v2 plus half z2 squared, right? And then when you do that, v3 dot will be v2 dot, which is this, which is minus x14 minus k1 z1 squared plus z1 x1 plus z1 z2 minus z1 phi1 dot, and now and z2 z2 dot, z2 into z2 dot, and z2 dot is u minus phi2 dot, right? Somehow I think kind of should have cancelled this and this term, but I think I kind of, once you do that, so this becomes z2 yeah, this term should have been cancelled earlier on and only, right? Because when this goes here, this term should not have been here. Yeah. For now, we'll verify later on, but let's say these terms are not there. Then it becomes minus x14 minus k1 z1 squared plus z2 outside. You have z1 plus u minus phi2 dot. Right? Now what will be u? U will be minus z1 and plus phi2 dot minus of k2 z2, and that makes your v3 dot to be minus x14 minus k1 z1 squared minus k2 z2 squared. That is, ladies and gentlemen, your u. You will see now, you will go and plug in what is phi2 dot, what is z2, that the u will become really ugly. But good thing will be when you simulate it and your math is right, that will be very satisfying, that if my v3 dot, now you have come 3 steps with this saying, hey, my v3 dot is negative definite, that means x14 goes to x1 goes to 0, z1 goes to 0, z2 goes to 0, that means in turn means x1, x2, x3 all goes to 0. And having such a kind of controller working will feel amazing. But it gives you so many tools, like now these tools were not there. It gives you very flexibility, a lot of flexibility here. Okay, got it? Good. Are you guys having some fun? Maybe this sliding mode assignment will give you some simulation fun, give you some understanding of what are the constraints of simulating nonlinear controllers and things like that. So you can always use S function kind of approach to just simulate x1 dot, x2 dot. And in fact, you don't need a separate controller. You can compute your u right in the S function itself, or you can have a separate u. Doesn't matter. Okay. So let me post the assignment now, and then you guys can due Friday. From
Did you not already post one that's due Friday? Yeah. Okay.
yeah, I'll just post it. Have you guys started?
No,
Let me
I
just
think
post
you already posted one that's due Friday.
the Simulink one. Did I? Yeah, I think I might have then. I might have. Let's see. If I not.
I have to submit also on Friday.
Like what?
I think I submitted, but I didn't. Friday and Saturday.
Oh, that was due last Friday?
Yeah.
Okay.
Yeah, I think assignments. What is this? You see. So special topics. Assignments. Assignment 5. And then
Yeah, I think you already got something due this, what's that, the 29th or the 28th maybe?
yeah, so that's yeah. I will post this for the next. So this will be due.
You have something that's already due the 28th posted, correct?
No, nothing is there on 4/28, 21st. So I haven't posted it yet.
Oh, okay.
Yeah.
I thought you
So
already-
assignment 6. Let me post it now. Name assignment 6. Due on 28th. Points.
I thought you did too.
Save and publish.
Maybe you just pulled it up and didn't post it.
Assignment 6. Why didn't it show up? Did I? Why it is not showing up? Assignments. 2 categories. Why are there 2 categories? Anyways. Edit. Files. Upload. Assignments. 6. Yeah. So let me post this. Edit. Files. Assignments. 6. Okay, so
I looked at it, I watched the videos.
dismiss all. Notify users. And submission online.
I thought you did too, but.
Maybe just didn't.
So what assignment was due? This is what you were doing yesterday, the previous, that was due.
We had something due past Friday, but I thought you already uploaded something that was due on the 28th. Because I remember complaining like, oh, more book work, and you said, no, there's coding in there too.
So this one is coding, I didn't think
It was book work and coding.
So this one is due.
I know
Yeah.
I saw it at some point. I don't know if you pulled it up or it was.
Yeah, I remember you pulling it up there.
Yeah, I
and
might have pulled it
assumed
up. So
you
yeah, this is
updated.
due this
Yeah,
Friday. So
Okay,
yeah.
okay.
This is the same one. Okay. And then we'll do a couple of backstepping problems. Of course with the implementation, and then we'll do the adaptive control. And then we apply them on quadcopter, UUV, and some examples. And some aerial recovery problem. So now, yeah, I think once we do these problems, maybe a quadrotor one and a UUV, you guys should think about what kind of projects you would like to do for this class.
Now, is that for a midterm?
Project is just a
There's
separate
two, is
quantity.
there two prod? I don't remember what the
So there is
says.
midterm, there is final, there is also a project. So 3 things.
Okay.
Because of
So a
these.
midterm, a final, and a project, okay.
And we have to put a date for midterm also. So let's say you need time, right? Spring break to prepare.
For midterm?
Mm-hmm.
When is that?
So I
Spring break,
think
that's what I
spring
heard.
break is
There's some lines, yeah, it's like mid-March.
my
13th.
15th March, starting 15th March. So you
Week after
see.
then?
What are you saying? Week after that?
No, he's asking, yeah.
After that or before that? It's on you guys. I can.
It's like, do you want to study over your
Yeah.
break or not? I will.
I think you should study.
I don't
on
have
this.
any-
I think
I don't have any plans.
you will need time to study things on this. So let's do after the spring break.
With that said, can you make no homework due that time?
Yeah.
Like actually
Yeah,
give us opportunity to study it? Okay.
yeah. So there will be no homework for spring break, but midterm preparation.
Okay.
Okay. Okay. Or if there is a homework, we'll put that deadline to 1 more week after
Okay.
this, after your exam.
Okay.
Should it not be the Monday we come back?
I was
Is
thinking the
that
same thing,
possible?
making it Wednesday, so we can
Wednesday
ask
would be
questions
cool.
on Monday.
Yeah.
Yeah, that's exactly what I was thinking.
Okay.
But will it be in person or will it be a?
We can just sit
Okay.
here.
Okay.
All right.
Sit here, or you guys can.
Okay.
Well, I can give a take home also. Like take home, you work on 1 or 2 days on it.
Take
Okay.
homes are always way too hard.
Yeah, I was like, I don't know.
You gonna be nice about it?
Yeah, of course. I'll be nice about it. So yeah, let's do. We'll work on that.
Okay,
Whether it will be a
okay.
take home or something. So it might happen that I can give you a take home, which you can work over your spring break basically, rather than.
We'll think about it. If we got options, we'll.
Okay, but yeah, take home is interesting here. Like it's you derive something, you implement something, and then show it in MATLAB.
Okay.
So I took analytical dynamics class and it was take home test. It was so tough.
Yeah, yeah.
Who was teaching analytical dynamics?
OM, McMahon.
Some graduate student.
Yeah.
Oh.
Kelly's graduate student.
He's in lab of Professor Black.
Oh no, with take home though, we got access to all your videos.
Everything. Open notes, open. Everything open.
Open friends.
That's not open. Just every notes, videos, everything is open except
So
it's an exam.
Oh, you would give us an exam over break, we'll open everything.
Yeah,
And give
open
us a
everything.
week to work on it.
Just come back on Monday and give it to me.
I'd consider that's okay.
Let's consider that actually.
Yeah.
So in fact I know what it is. It will be. So we will do a similar problem. It will be an adaptive backstepping control. So we will solve that problem in 2D in class, and you will extend to 3D in your spring break.
So I thought adaptive and backstabbing they are all.
See, sliding mode and adaptive are when you are taking norms, right? How do you show that something is negative definite? By choosing u. So choosing u equals to minus something into sine of s makes it sliding mode. In adaptive, you will have to basically go and also get that parameter being estimated basically. So adaptive will be different pairs. Backstepping an approach of how do you go from this step to this step and how
Can
if
be
my
applied
u is
to
here.
both, right?
So yeah, both adaptive sliding, sliding backstepping, and adaptive backstepping. Backstepping is just a mathematical rule of reaching up to that point. So before that, I think till 15th March, I think we will have good enough assignments to give us that. And then final exam, we can do in class, simple basic concepts, 1 or 2 line of differentiations.
I just hope your midterm isn't anything like the homework, because the videos aren't helpful for the homework.
Videos are not?
Not for the homework. I don't think so. I think the homework is very hard.
Yeah, it's your exam will not be like that. Exam is always I'm making them, so I want to give questions which I can solve. Okay. Yeah, so think over it. I think most probably we'll go for take home route and give you flexibility, no pressure kind of deal, right? So.
Yeah, I think that ensures we learn it,
Mhm.
as opposed to personally, but.
And then final we will do like, because a composite test of coming up with, okay, is it asymptotically stable, it's stable, not stable. Very simple, small problems, doable. Okay? All set then. Thank you. I'll post this video.